All right, here's 5-3, day 1. We'll really explore two topics in 5-3. One is the idea of a conditional probability, and the other is independence. You can see in this first question, we've got some data here we already know, by the way. We had said being a homeowner was event A and a high school graduate was B. If we know the person owns a home, okay, this right here is what we call a condition. We know the person owns a home. What's the probability that they're a high school graduate? The way this would be written would look like that. This vertical line can be read given that. So we're looking for the probability of event B given that event A has occurred. Okay, that was our condition. So that what comes after the given that is always your condition. Start down on the bottom because a condition always reduces the sample space of the problem. This is not about all 500 individuals in our set of data. It's only about the homeowners. Okay? Of those 340, how many were high school graduates? 221. Comes out to be 0.65. Second question is just reversing it. What's the probability of A given B? Okay, now we're saying the condition is that they're a high school graduate. This is going to be a different probability because right off the bat the number on the bottom changes because this is only about high school graduates. There's still 221 that fit both. Okay? And that would be like 0.71. Let's do some more of these down here. One thing we're going to want are the totals. I'll write those in. I have them. They're all pretty big. $3,392, 2,952, 3,656. There's 6,300 liberal arts students, 1,600 in engineering and physical science, and 2,100 in health and human services. Giving us a total of 10,000. Okay, so here we go back to on this first question. By the way, it defines the two events. That E is that we selected a grade that came from an engineering and physical science course, and then L is the event that's lower than a B. So here's event E, here's event L. Those are the two that we're going to discuss. L is just the probability that we have a student that obtained a grade lower than a B. That is not a conditional probability. And that number is, again, the probability a student, any student, in fact, I might reword this a little bit because I think the numbers in the table aren't necessarily students or grades. So I'm just going to say that instead of selecting a student, the probability that a randomly selected grade is lower than a B. Running out of room. Got it. All right, so again, that one was not a conditional. Okay, these two are. The probability of E that you selected a grade from an engineering and physical science course, or L. I don't want you to worry about the explanation. I just want you to calculate these two. Always over the condition. Okay, always over the condition. Okay, and then on the top you would have, and you're only looking at that category of grades that were lower than a B. 800 of them were in engineering and physical science courses. That's about 0.22. Up top we'll have 800, but now this is just about the engineering grades. There's 1,600 of those, and that one comes out to be 0.5. All right, this whole conditional thing can be a way of testing in a property called independence. Okay, so I'm going to summarize what it gave us here. That event B, I think this might have switched what I called them the opposite. So just for this example, we don't need to go back to the table. Just go with what they're calling the events. Probability that somebody owns a home was 0.68. If I threw in the condition that they were a high school graduate, the probability changed. Okay? You will see that if you calculate an event and then you calculate it again under the condition, and if they are still the same, we are able to establish that A and B are independent. Okay? Now look up here. 0.68 does not equal 0.712. Okay, so for the problem we were doing, we could use that as evidence that A and B are not independent. Okay? Independent meaning the outcome of one doesn't impact the other. Okay? We're not able to say that. But conditional probabilities can be very, very helpful in justifying if events are independent or not. If we were faced with a question like this, based off this data, are the events of being a female and having allergies independent? So first of all, let's just talk about independence a little bit. If events are, it means the outcome of one does not impact the other. Okay? So in this case, what we're looking at is if you knew somebody was female, would it make them more or less likely to have allergies? Okay? If it doesn't change the odds at all, then we'd say they're independent. Okay? But here's what you should check if you're testing for independence. And it doesn't matter which way you do it. It's given us two events. We need to calculate the event and the condition. I'm going to say female is event A, allergies is B, and I'm just going to, you could use either one of these, but I'm going to use the first one, okay? The probability that a randomly selected student is female is 23 out of 40. What about the probability that they are female, given we know the student has allergies? Okay, given we know they have allergies. Well, there's 18 students in the table that have allergies. Ten of those are female. And now it becomes a question, are these two fractions the same value? If they are, we'll say they're independent. If they're not, you should immediately switch them to decimals. So here, there's a 0.575 chance we'd select a female. And a 0.556. Now those are really close, but we're really strict about it. We're going to say that these events are not independent. 57% chance that we were to pick a female, but once we knew the student had allergies, the odds it was a female student went down slightly. Basically meaning that under the condition, the odds you were going to pick a female, they were reduced. Just a little bit, they were reduced. Okay, here's more of them. All right, standard deck of cards, turn over the top card, put it back on the deck, shuffle again, and then turn over the top one. Okay? Is the probability of B the same as the probability of B given A? A is selecting a heart on the first card, but it's put back. So for the second card, it's 13 out of 52. But even if you drew a heart on the first one, you put it back and shuffled, so the odds stay at 13 out of 52. Okay? So here, as far as independence, you could say yes. Okay, so putting the card back and shuffling makes the selections independent. Okay, it doesn't matter what you got on the first, your odds of the next one are going to stay the same. Now look at this one. Same context, same idea, except don't put it back. Okay, B is just selecting a heart on the second one, but it doesn't say anything about the first. So it's almost just like selecting a heart. Okay, so I'll just say 13 out of 52. Okay, because it kind of just doesn't factor in event A. You're not worried if it did happen or it didn't happen. The odds of selecting a heart are 13 out of 52. However, if the first one was a heart, there's only 12, for the second draw, there's only 12 of them left out of 51. Those probabilities aren't the same, and you would say no. Okay? Good one to illustrate the difference, that if you're dealing with a deck of cards, the selections will be independent if you're replacing the cards after each draw. If you're not, then they're not independent. The odds of what you're getting on your second draw depend on what you got on the first. The events of interest are female and right-handed. Again, we've got our two-way table here. We're going to say female is A, right-handed is B. 21-7, 4, 24. This is out of a class of 28. Okay? Let's calculate the probability we select a female student, and then the probability we select a female student under the condition that we know it's a right-handed student. Okay? To say that these two events are independent, these probabilities have to be the same. Okay, so now if it's right-handed, we're only looking at those 24. And out of those 24, 18 are female. You switch those to decimals, and you say, hey, they are the same. Those events are independent, being female and being right-handed. Okay, have nothing to do with each other, right? So, and again, think of the numbers this way. Hey, what are the odds we pick a female student? 75%. Oh, wait a minute, though. I'm going to give you a hint here. The randomly selected student is right-handed. Did that change the odds it was a female? No, it's still at 75%. All right, I'm going to show you how to draw a little tree diagram to work through some other, for selecting two. It's the same data as an allergy problem that we did earlier. Here's what a tree diagram would look like, because we're going to select two students. Here's my first draw. There's allergies and not. And here's my second draw, allergies and not. So this would give you my sample space. Both students have allergies. First one does, second one doesn't. I should use that notation up here too, because these are both and, right? Because by the end of the tree diagram, I'm saying both of those happened. First draw, allergies, and second one had allergies. First one had allergies, and the second one didn't. Okay. Now you can throw in the probabilities too. 18 out of 40, 22 out of 40. The second branches are like conditional probabilities because it depended on the condition of the first. Okay, if you selected a student that has allergies in the first draw, this is 17 out of 39. This one's 22 out of 39. These branches down here represent the first selection. That student did not. So the second selection for a student who does is 18 out of 39. And this one would be 21 out of 39. All right, so I could go through and calculate all the different possibilities if I just follow the branches in the diagram. I'll do one. You could certainly go fill in the other three. Here's the event it's talking about. So I'll follow its path through the diagram. There and there. There are the odds the first student did, second student did. Multiply those, and I get 0.196. Okay? You have three other probabilities that you could calculate in a very similar fashion. Okay. First set of branches here is going to be sport or not in high school. And it said that breakdown was 0.55 and 0.45. Of those who played sports, right, so this second set of branches, again, is conditional, right? This is given the student played a sport in high school. At the college level, there is a 5% chance that they continued to play. 95% chance that they didn't. Doesn't really say anything on this, but I'm assuming this is basically if they didn't play in high school, no chance they played in college. Maybe a few weird cases here and there, but I feel okay with those numbers. What percent of high school students played a sport in high school and go on to play in college? What's talking about this? S and S. It meets both of those. So this would be 0.55 times 0.05, which is 0.0275. Under 3%. And a randomly selected student from high school would go on to play a college sport. All right, one more tree diagram, and then we'll call it quits for our first day here. All right, so the first set of branches is going to be their media use. Low, medium, and high. 17% said they're low media users, 62% said they're medium, 21% said high. Now we have all these conditional probabilities off of their grades. For those who said, right, this is their grades given that they said that they were low media users. Good, not good. The breakdown would be like that. This now has the condition of medium. 0.68, 0.32. And your high media users, 52% said good, 48% said not good. Okay, what percent of young adults describe their grades as good? Well, I got 3 different outcomes I got to add up. I'm going to highlight the tracks that I want. Low use and good. That was 0.17 times 0.74. I want to know them. You've got medium use and good. That would be the event M and G. 0.62 times 0.68. And then you have your heavy users with good grades. That would be H and G. 0.21 times 0.52. Okay, I want to include all of those in my answer because those make up all the students that said their grades were good. Add them up and add them up, and we get 0.656 said their grades were good.